Let g defined from R to R be the function given by g of x equal to mod of x raised to x if x is not equal to 0 and equal to 1 if x is equal to 0. Then g is differentiable at 0. G is a strictly increasing function on R. G is continuous at 0 and g of x is equal to 0 for some x in the set of real numbers. Okay, alright. It is a multiple select question, so more than one options could be right, and this appeared in 2019 second shift. Okay, so let us write down the function again. G of x is equal to box x raised to x. Okay, if x is not equal to 0. Okay, so which one is which option you are looking for to start with? Let's think of D now. Okay, suppose we are investigating whether D is right or wrong. Okay, it says g of x equals 0 for some x in the set of real numbers. Now look here. Okay, at 0, what can I say? G of x, it is 1, so definitely that is not equal to 0. Okay, so we can now say at x not equal to 0, or let's say for all values of x, okay, in R minus 0, do you agree that box x will be positive? For all values of x in the set of real numbers excluding 0, box x will always be positive. Yes, we know that. Okay, box x will always be positive. Now, if a greater than 0, then a raised to x will always be positive. So for all values of x. Raise your hands if you understand this. Second point. If a is positive, then a raised to x will be positive for all values of x. Which means we have proved conclusively that g of x will never be equal to 0. So D is not right. Okay, D is not right. Okay? Now let us go for option C. Okay, yeah, because logically domain and codomain range come first, then continuity, and then differentiability, and then strictly increasing function and all that stuff. Okay, okay, let's go for C now. It says G is continuous at x equal to 0. Okay, let us first find the right hand limit. Okay, let us first find the right hand limit. Let's call it L1. Okay, let us call it L1, and what would it be? Limit as x tends to 0 plus g of x. Now look, if x is positive, then mod x will be equal to x. So I can write this as limit as x tends to 0 plus x raised to x. We can say because mod x is equal to x if x is positive. Okay, let's take log now. Okay, let's take log now. Ln L1 equal to limit x tends to 0 plus x ln x. Okay, x ln x. Now look here, in which indeterminate form is this particular function in? It is in the indeterminate form 0 into infinity, because ln 0, well, limit, right hand limit of ln x as x tends to 0 is negative infinity. Okay, so is there any chance to write it in terms of an indeterminate form in which L'Hospital applies? Yes, let us go for this. Now in which indeterminate form this function is? It's infinity by infinity. But don't worry about the negative sign. Okay, don't worry about the negative sign. As long as it is in that indeterminate form, L'Hospital rule applies. derivative of log x 1 upon x, derivative of 1 upon x negative 1 upon x squared, and this is now in, well, not in the in any indeterminate form. It's just x with a negative sign, so the log of the limit is 0, so limit must be 1. Okay, so at least the RHL is equal to 1. Okay, do you understand this? RHL equal to 1? Yes? Raise your hands if you understand. Okay, RHL is equal to 1. Now let us go for LHL. Okay, let us go for LHL. Okay, LHL, let us call it L2. This is limit as x tends to 0 from left g of x. Okay, so what would it be? Limit as x tends to 0 from left negative x raised to x. Why? Mod x is equal to negative of x if x is negative. Now here is one change that I'm going to make. I'm going to say let negative x be t. So x will be negative. Okay, so if x is approaching 0 from left, negative x will approach 0 from right. Okay, so it will be t raised to negative t. Okay, t raised to negative t. Now look carefully how I am making the adjustment. I am going to write it as 1 upon limit as t tends to 0 plus t raised to t. Because I know that limit exists. This is nothing but what? That is nothing but L1. Correct? That is L1. And what is L1? 1. So this is also equal to 1. And because L1, L2 and f of 0 are all same, therefore L1, L2, they are both equal to 1. Therefore this option, whichever it is, C, that is right. It is continuous. Okay, C is continuous. Okay, so have you understood how we concluded that C is right? Yes? Okay. Now between A and B, okay, let us go with A now. Okay, let us go with A, because suppose if we find that G is not differentiable at 0, then there is no question of it being strictly increasing and all that stuff. Okay, so let's go for A now. Okay, let's go for A, which says G is differentiable at 0. Okay. Now, suppose we go for the right hand derivative. Okay, suppose we go for the right hand derivative at x equal to 0. So let's take the function g, and now we can write it as x raised to x. Okay, what is log of g? It will be x log x 1 upon g into g dash of x is equal to 1 into log x plus x into 1 upon x, product rule. So that is ln x plus 1. Okay, ln x plus 1 into g, okay, of x, of course. Now look, at x equal to 0, what are we getting? Ln 0 plus 1 into g of 1. G of 0, which is ln 0 plus 1 into 1, because g of 0 is 1. And is this defined? It's not defined. Have you understood this? That ln 0 is not defined, and therefore the right hand derivative is not defined, and therefore g is not differentiable at x equal to 0. Okay. g is not differentiable at x equal to 0. Raise your hand if you understand this. Now, some people may argue that we have used the other definition that g of x is equal to x raised to x. How can we conclude with that it is not differentiable? Okay, note that it is continuous at that particular point. Okay? And suppose if you are not convinced, then what you can do is you can use the first principle and you can try it for yourself. H tends to 0 plus g of h minus g of 0 upon h. Okay, so you can try this limit, tell me what value you get. Okay, h raised to h minus 1 upon h. Okay, so do you think you can solve this particular problem? You can take it as homework and tell me what value of limit you get. Yes?
Okay, sir.
Okay, you will still, I think you will still apply the L'Hospital's rule there. Okay, let's do it. You'll still apply the L'Hospital's rule there. Because h raised to h limit as h tends to 0 is 1. Okay, and now I will show that to you here. Look, x raised to x's limit as x tends to 0 is 1. Although now it is showing that it is defined, clearly 0 raised to 0 is not defined, but the limit is 1. Okay? So L'Hospital's rule applies. Okay, L'Hospital's rule applies. Derivative of h is 1. H raised to h derivative, we have just found it out. It is ln h. Okay, ln h plus 1 into g of h. Okay, and again you basically get the same result there. Because the log of 0 is not defined, ln h is going to be negative infinity to negative. Okay, so option A is correct. Well, as in our conclusion regarding option A is correct. Now, if it is not differentiable at 0, can we ever consider to be strictly increasing? Can we ever consider it to be strictly increasing? No, we cannot. Okay, we cannot consider it to be strictly increasing because simply it is not differentiable at one of the points in its domain. Still, suppose you didn't know whether it is differentiable, or suppose option A was not there. How would you conclude that g is not strictly an increasing function enough? See, look, let's momentarily break our solution here and continue discussing from there. Okay, look, suppose x is 1 upon e. Okay, suppose x is 1 upon e, then what would be g dash of 1 upon e? That is 0. And for strictly increasing functions, derivative is never negative or 0. It is always increasing or always positive derivative. Can't be 0. So that option B's validity is also this one. Got it? Yes? So in NEST you have to be careful in solving the multiple select questions because it may be a multiple choice question in disguise. Okay, like this case, but usually more than one option is correct for such questions. Okay, but anyways, wanted to include that, and we have conclusively proved that it is only continuous but not differentiable at 0.